to do is really just kind of finish up well, what I want to say about non-relativistic quantum fields. And the main thing is to just kind of go over the story of what how symmetries work with these things from the point of view that I've been taking in this class. And I said a little bit about that last time, but we'll do that more completely this time. And depending on how much time I have, there's also a chapter in the book which is kind of much more general comments about quantum field theory, which I'll try to say a bit about, but I probably won't get anyway. So what's in chapter 39? I may say a little bit about it, but it's there's some that's a bit more kind of a survey of just kind of some more explanations of kind of what goes haywire in quantum field theory and why in general. There's a lot of phenomena in quantum field theory which are kind of new and hard to deal with. So I just kind of wanted some of that is just more comments about that. Okay. Oh, and okay. So let's get started for today. So part of what I'm doing is just reviewing a bit about what I kind of said last time, which is the main idea is that so that even in finite dimensions, the story I was trying to say was that if you took a phase space, complexified it, and you got what do I call it? I guess I called it there m plus m minus. Once you chose a complex structure, and then the idea was that that on this thing you were starting out with a group of symplectic symmetries of S. Let's say this has dimension 2D. Let's say. Then here you had how do I want to do this? Here you had. Well, if it was fermionic, if it was bosonic, you had an SP of 2dr. If it was fermionic, you had an O of 2dr. Bunch of symmetries of the situation depending upon the kind of Poisson bracket or antisymmetric or symmetric gadget that you had on here. But then once you chose this, once you chose this decomposition, that picked out a subgroup U of D here. And what we're interested in is groups that lie inside the subgroup that act as unitary transformations on this. But what we're doing, what we're doing in QFT, or at least non-relativistic QFT, is we're taking M plus is H1, which is the space of solutions to the Schrodinger. Okay, and actually just the free particle. And then M minus is H1 bar is the same space where you complex conjugated everything. You've taken the scalars to act by multiplication by their complex conjugates, and you just have a map that takes everything in here and everything in here just by conjugation, and vice versa. And so this is going to be kind of an infinite dimensional example of something that here you'd have a basis of these ZJs, and here you have the Z bar Js. But what we're doing now, the problem is that the dimension. So the problem is that we've gone to infinite dimensions. So you have to be this is what creates all sorts of trouble. And as I said, the one way to get around it is just to kind of put cutoffs in and assume you really are in finite dimensions, and then take a limit. You can always do that, but it's going to be this is the source of the problem. And here, but here we're so you have so we're interested in finite G, which are lying inside U of infinity. So in some sense, the kind of group of symmetries of this thing is going to be a unitary group. It's the unitary group of of all the unitary transformations acting on these spaces. So these are complex vector spaces with an inner product, and the group of all linear transformations that act on these spaces, preserving the inner product, is infinite dimensional. But we don't actually want to kind of, this is kind of too horrible to think about. We don't want to actually try and discuss this group explicitly or what its representations might be. But what we're interested in is certain cases where where there's some finite dimensional group, which we'll recognize as a group of symmetries of the situation. And what we want to think of that as lying inside here, and the Lie, and we'll study representation of G, on the state space, and we're using the Lie G is going to be quadratic. So what we're going to do, so this guy is kind of hard to think about, but one way of thinking about it is that the Lie algebra of this guy is just going to be the Lie algebra of all kind of homogeneous order 2 functions on this guy, or on the dual of this guy, if you like. And that's, and so what we're interested in anyway. But there's an infinite number of. This is still an infinite dimensional vector space. It's the Lie algebra of this infinite dimensional group. But we're going to be interested in the plan is to just identify which quadratic functions correspond to certain symmetries acting on the situation, and then once we've found those quadratic functions, just turn them into operators. Quantization is just turning these things into operators using the field operators. Okay, so that's the plan. And then so I want to kind of go through this story. Okay, and we're going to do this just for some of the kind of obvious symmetries, kind of space-time symmetry, space-time translation and rotation symmetries, and various kind of internal symmetries. So let's talk about those. And the first one was I started talking about last time, which was the Hamiltonian. So G is equal to R, which is the time translations. Symmetry. Okay, so just T goes to T plus A. So you just okay, and okay, so the question is, so how does this symmetry, the symmetry act on the space of on the space of solutions? So you want to say so how does this act? So the action on H1. Well, it's a little bit confusing because you know that solutions look like e to the I. So a basis of solutions is these things times e to the minus I t I to 2m t. So you explicitly know what these solutions look like. That this is what they look like, and they for all p. So this is a basis. But you have to somehow kind of ask yourself, okay, how am I going to think of, okay, how am I going to put coordinates on this space? And what's often a good idea is you often so you can identify to associate a solution to initial data. So this is going to be so this guy is then going to go to just e to the IPX. Okay. So you can think of all these. Sometimes I'll say, well, I just think of this space is this is a space of functions, and it's just the kind of doing the usual thing. I'm just looking at complex functions on the real line, and I'm thinking of those as the t is equal to 0 initial data for solutions. And then I want to, and Fourier analysis tells me that I can write all, in some sense, the e to the IPX are a basis of these things. Okay. Okay. So, but now the problem is, so this creates a little bit of a confusing situation. If you ask, okay, how does the how do T translations act on this guy? Okay, so what they're going to do, so T translations is the T plus A. Well, what it's doing is the actual solutions are going are behaving like this. So T plus T plus A as a solution goes to well, e to the IPX goes to e to the IPX squared over 2MA, right? It's just multiplied. Just these basis vectors are just going to be each getting multiplied by this phase, depending upon P. But if you want to this is where I always get confused. I'm not sure that I'm a little bit afraid that I've got to give an explanation of this. Is that that gets this backwards? Let's see. Okay, so here's the problem. Maybe this is what I mean by having it backwards. So this is what happens on solutions, but this guy. Okay, now somehow what I want. So initially initial data. Plus, yeah. So what let me let me just maybe leave this as saying that you have to watch out that because of the way how you're defining this, you have to figure out what you have to define what does it mean to act on the space of initial data.
You mean you map E IPX times E negative IP square over 2MT to E IPX E times positive IP square over 2MA?
Yeah, positive, yeah. So I'm just saying that, yeah. So
I mean, the left-hand side, you should add the term E to the power negative IP square over 2MT.
No, well, there's no T, there's no T's. So this is what the solution is.
Yeah, I mean, yeah, so the left-hand side will be a solution for like how I see a T.
Okay, and so this guy.
I mean, left-hand side to the arrow.
Yeah. So somehow what always confuses me. I thought I Now earlier today, I thought I had the right explanation for this, but now I'm not so sure. So the only problem really is there's a sign problem here, which is really annoying. And it's kind of, the question is, what are you going to do? Okay, if you actually have the solutions in this form, then it's easy to see how you're going to translate. If you try to translate t to t plus a, I just add plus a here, but then it's going to appear with a minus sign. But you have to realize that the way I'm describing solutions is not this way, but I'm describing them as by their initial data. Okay, and so a trend. So, but on the other hand, I'm trying to take the solutions. I'm trying to claim that there's an action of the real numbers of of the real numbers on
Yeah, just so it's a representation on functions. So isn't it? Don't you act by the inverse on the arguments?
I don't.
So that would give you the right sign.
Yeah. Okay. Yeah. Let me. Yeah. That may be right. I'm trying to remember. See, the problem is there's that issue about are you acting on function? But no. But the I don't think that's. Let me just say this also. There's a related issue. Which is that we want to be in the Heisenberg. So we sure. So the idea and there, sorry, did I write this last time? Yeah. So there you had where did I? Anyway, so there you have so operators depend on time. So states don't change in time, and we have what? We have ddt of the operator. Operator H. Okay, right. So this is the and so if you think about what you're doing here, one way of thinking about what you're doing is to it's kind of related to this, is that the what you're doing is whenever you're trying to figure out, whenever you're trying to deal with an operator at a given time, it's not time at t is equal to 0. What you have to do is you have to conjugate it. You have to move it back to time is equal to 0. Evaluate, see what it does on the time is equal to 0 states, and then move it forward back to where you are. So you get a conjugate. So there's the Heisenberg picture operators are defined by with respect to the Schrödinger picture operators by a conjugation by e to the it. But really, what you can, one way to keep track of what you're doing is you're trying to keep you're trying to move. If you to study what it's doing at a given time, you're moving it back to time to 0 and then back. And so that process means that this thing then depends this operator. And what I want is and in particular for the operator is the field operator. What I want if you work this out, you find out that the field operator x is equal to hat of let's take this one. A hat of the one that's at t at time t. Well, let's make it 0 t. So the relationship between actually, sorry, I should take, maybe it's better not to work just a momentum space. So A hat 0 of t p is this guy times e to the I p squared over 2m. Okay. So it's going to be that. So yeah, this is the same kind of issue. Anyway, there's a similar issue here, and but the problem is that there's several sources of an inverse minus sign. There's the one you mentioned. There's the fact that you may want to think about these things as distributions, and then there's the fact that you're in Heisenberg picture, and so you're trying to represent your states as states at t is equal to 0 states, but you're trying to describe the t translation action on those states, and anyway, so the sign of which direction you're going in t can get very confused. And I believe, at least the statements that I make in the book, at some point I believe that they were all carefully checked, but it can be confusing exactly which one it is. But this should be a fairly straightforward story, except for the sign. I mean, the only thing that you should be able to guess exactly what all these formulas are going to do, what they're going to look like, except you may have to think hard about the sign. Okay.
So these like time translation symmetries are somehow acting on the space of like operators on the state space.
No, so okay, so what you've got is well, actually there's maybe even a similar confusion, maybe even a little bit in classical mechanics, but you've got it's just you've got a phase space, and one of the basic, I mean, one of the basic kind of symmetries of the situation is time translation symmetry, and it's the Hamiltonian. And its question is, what generates time translation symmetry? That's your dynamics. That's your Hamiltonian operator. So I want to, so I guess I was going to say this in a minute, but so the trick is, figure out what's the one thing you want to do is to figure out what's the Hamiltonian operator that that's going to do this. And so we'll go over that again quickly. But you can understand what's going on here as anyway, you can understand what's going on here as kind of the story about this symmetry and about the quadratic operator that generates it, except but you're not, I mean, that you have to be told. Somebody in some sense has what kind of determines the theory is kind of somebody specifying what the Hamiltonian operator is, which is going to tell you how you're going to move in time. And if it's a free particle theory, then the Hamiltonian operator is just going to be this quadratic thing. And let me go over that again. So I think let me mirror this. And so the story at here was that the Hamiltonian, in this case, which I also wrote, I guess here I also put a hat on to say it's the Hamiltonian for the theory of the on the multi-particle state space, on the Fock space. It's the and you basically integrate a dagger P A P. Okay, so what this is, so this is really just, you're just kind of integrating the number operator over the p's, but then you're associating this the p squared, but then you're giving you're multiplying by the energy corresponding at p for each p. So this is the operator. So this is the operator. In some sense, this is the thing that's supposed to have eigenvalues that are the energy. Well, this guy times this guy is supposed to be the thing that's counting a number of states with momentum p, and this is the energy that they had, that something with momentum p has. So this has to be the operator that you want. And if you Fourier transform it, you get sorry. Yeah. Anyway, and if you Fourier transform this thing, you get the same thing. But then there's a 1/2m p squared dx. I guess there's a Mars a minus. Okay. So this is this you know is a lot easier to understand kind of physically. You're just counting the number of these nice momentum eigenstates, which are always going to be there, and then and weighting them by the energy. Here you're doing something funnier. That here again, this is something which in some sense is creating something completely ill-defined, which is a state at x is equal to 0, and then it's annihilating a state at x equal to 0, creating one here. Anyway, and you've got a and then. But then you're measuring the energy by this differential operator, which is not really quite not diagonal in x, but it's it's this. But it's exactly the operator that you see in the Schrodinger equation. Okay.
Are these the time independent operators at time equals 0?
Yeah.
Yeah.
So we're assuming in this case we're always assuming that the Hamiltonian is a time independent operator. Yeah, because if the Hamiltonian is not a time-independent operator, then the whole kind of story about the Heisenberg picture, well, the problem is you can't kind of just exponentiate. Yeah. Anyway, yeah, the standard problem with if you try and exponentiate an operator that depends upon time, you have to do something much more elaborate. But yeah, so we're always going to assume the Hamiltonian is time-independent. Okay. And then maybe just a few comments about these formulas. So what's really so if you try and manipulate these things, you really have one way of manipulating them is to just kind of put in cutoffs and act as if this was just the sum, and this is then just some linear operator. But if you just discretize the problem, put in cutoffs, and then this becomes a large diagonal matrix. This becomes a large, not quite diagonal matrix, but just that relates to nearest neighbors, and then you can just work with those matrices and use the annihilation, use the commutation relations and things that you have in order to do calculations. And the states are just kind of big collections of harmonic oscillators. If you want to work in the continuum, then you have to remember that what really makes sense is a dagger of F P F. So that or the same thing. So and that F is some nicely behaved test function. F is like say a Schwartz function. So the things which really so these formulas are kind of formulas involving distributions really, and that if you really want to make sense of these, you have to kind of feed you have to feed these guys nicely defined Schwartz functions, and then you're going to get you're actually going to get well-defined operators. And if you want to know what those operators are, you can. The Fock space construction says that this operator is basically given by taking well anyway you're basically the Fock space construction says you're moving your Fock space is this big tensor product. You're moving up one degree in the tensor product and then just tensoring with this function f, with some function f, so which is some function on the possible on the single particle state space, and then that's so this point is that if this is true, what's well defined is not, this is not well defined, but there is such a thing as this guy is well defined. Similarly, this guy is not well defined, but there is such a thing as this that are well defined. And the thing that's the tricky thing about these formulas is that they've actually got two operators in them, and this is where you get into trouble whenever you're trying to talk about distributions. That when you start multiplying distributions or multiplying distribution valued operators is a funny thing to be doing. But what you can do here, so you can handle quadratic let's say it this way. You can handle operators, distribution, operator value, distributions. Like these, they're quadratic. Let's say this way, of the form. Oh, if you've got an operator, a distribution valued operator, and then some of a certain kind, and then some another kind of an adjoint. The point about these guys is that you're interested in in sandwiching these things on states. Let's call this phi. I don't know, 1, phi 2. Okay, so what you do is you can think of this. So this guy, if you feed this guy a Schwartz function, then this guy is well defined. If these are nice states that you've gotten, these are well defined states in your state space which you've gotten by taking the vacuum and applying various operators, with corresponding to various nice Schwartz functions to this guy, to nice wave packets. You're going to get some nice state here which has all the nice properties you want. But then your problem would normally be that if you try and multiply this operator, let's say for some other Schwartz function, if you try and multiply two of these guys, it gets very confusing. What is it really? What does it mean? Multiplying two distributions it causes all sorts of troubles or all sorts of confusions. But what does make sense though is this guy. That this guy is O of G plus A2 kind of adjoint, right? Okay. So the point is that for kind of quadratic things of this kind, you can actually make sense of. You can if you want to kind of get rigorous and really say, what exactly do I mean using, rigorously defined operator operator value distributions for well-defined Schwartz functions. What you would need to do in this case is think of the thing which kind of works for problems which have the structure of kind of annihilation operators over here and creation operators over here. Is that these guys, you make sense of what these guys do if they're you know, if you feed them some nice Schwartz function, and you make sense of what these guys do, if you feed them some Schwartz function, but on states on the other side, and then so these guys make perfectly good sense. These guys make perfectly good sense, and so you're just and these are all states that have well-defined inner products. These are states. The Schwartz functions are things that have a well-defined notion of inner product. With you could take the adjoint of the state and anyway, and then compute the inner product of these guys. Anyway, so this is not something you normally want to do. If you're trying to think about what's going on or trying to do a calculation, it's, I don't recommend trying to go through this exercise and really trying to understand exactly what these states are. I mean, what you find in people doing quantum field theory calculations is they really go to a lot of trouble to avoid ever explicitly doing this or explicitly thinking about what these states look like, because it's a long story and it's fairly complicated for anything you're interested in. So what you're actually, manipulations you're pretty much always going to see, what people are always going to be doing are going to be working with these distribution, with these symbols, and what you end up doing is you end up doing a bunch of calculations with these guys, which are then used like their commutation relations. So you have to. So if you want to think about, again, this is part of the story. What sense does it make to multiply two of these guys? Well, anyway, if you want to make sense of, you can make sense of multiplying two of these guys using this method, and then the basic kind of property they have is that the answer you get here, if you take this distribution times this distribution minus them in the opposite sense, you end up with something. In general, multiplying distributions is hard, but the difference between these two things is something well defined. But what it is it's also a distribution. It's a specific delta function distribution. So the whole game of doing calculations in these theories involves kind of working with these symbols and with these kind of distribution valued, realizing your distribution valued operators, and trying to just to bring everything down to the commutation relations, and then to use the fact that these things have a well-defined commutator, which is also a distribution, and as long as you don't try and calculate the wrong thing at the wrong time, you end up with you can get sensible results this way. And if you want to ever really check, is this really actually making any sense? Your two choices really are: one is to just discretize, work with a discrete set of p's, and then take the limit, or do this, work with real Schwartz functions and be careful about very, very careful about which states you're talking about, and about exactly how these operators are acting on these states, and then be sure to apply the right operators to the right states. And if you do that carefully, you can also end up, then you can rigorously end up with reasonable results. Okay. So anyway, this was just kind of a warning about rigor. I wanted to at least once kind of, so from now on, you'll see, I'll do lots of more dubious calculations using these kinds of relations. But I wanted to kind of, to say what the legitimate story is at least once. And
question.
Yeah.
Maybe it's naive. So is H, is this the Hamiltonian or the Hamiltonian density?
This is actually, you would say this is the Hamiltonian density, but the integral, this is the whole thing is the Hamiltonian. Yeah.
Okay.
Yeah. And so, And these formulas look very much, one reason for writing these formulas this way is they look very, very much like corresponding classical things. So there's if you write, if you think of a corresponding classical theory, and I think maybe this is something I never really said as much about it as I should. There's you can think of there as being a corresponding classical theory to this, and the corresponding classical theory is again just the one with the okay, but there's something funny about it that anyway, this is a funny classical theory again, because remember what I was trying to say is that claim is that, well, is that I want this. Okay. So this is a very simple thing. It's just the solutions to the free particle Schrodinger equation. This is just the complex conjugate, or if you like, it's the solutions. It's the solutions with the up to the Schrodinger equation with the opposite sign. But the and so these are nice well-defined spaces. The problem is that if you want to think of this problem as coming from a nice classical problem with a standard kind of real phase space, then you have to somehow ask yourself, okay, well, what's the real, what's a real space, which if I complexify it would give me this. And so you end up looking at something. Anyway, this maybe gets very confusing, and I think the right way to think about it is that it's just not. And maybe another way of saying it is that you want to think of this guy as phase space. Okay, and if you ask for the anyway, if you ask for, if somebody gives you the Schrodinger equation and says, okay, I want to take, let's take the the space of solutions of this equation, let's take this as a phase space. Your problem is that, remember, it's a first order equation. So when you have a first order equation, so often you want to think of a phase space as being the thing which the Q's and P's which tell you, which correspond to all the initial data to you need to get a solution in the equation of the equation of motion. But normally you're used to thinking about second order equations. So then you've got configurations variables Q and momentum kind of variables P, and you need both Q's and P's because you need to say what some initial data and some first time derivatives. The thing is, but this is a dynamical system which is first order, so you don't actually have, there isn't any way of really kind of naturally breaking it up into P's and Q's. This is the problem with this, with thinking of the solutions of the Schrodinger equation as a phase space, is that it's not a kind of phase space that comes with a decomposition of Q's and P's, because it's a first order equation. So it really is. So all you can really do is kind of think. Well, I mean, anyway, if you look, if you look in the book, I explain at various points, different ways of thinking about, if you do this, then you can identify. You can then you can identify in some sense this space with this space. You can think of this space as this space with a complex structure, as with a complex structure given by J. But it gets very confusing here because these are already complex spaces. So there's a story you can tell about it. But I think if you look anywhere in the literature at what people do when they talk about this theory, so sometimes you'll see people writing down saying, okay, well, let's do the quantum field theory for the non-relativistic case. But then the methods that they're using often depend upon assuming that you have a second order equation. They're assuming that you can divide things up into P's and Q's, and the whole kind of Lagrangian formalism really, anyway, the whole kind of Lagrangian formalism is kind of based upon having a notion of what are the configuration space variables. And here the problem is there is no distinction between that nice way to break these up into configuration and momentum space variables. So you end up with kind of, if you try and treat this in kind of the standard formalism that people are used to for writing down the kind of classical canonical formalism and then quantizing, you'll see some funny things happening. And one thing, so people are realizing that, wait a minute, they try to find the conjugate momentum to psi and they find that it's psi bar. But wait a minute, psi bar and psi aren't actually independent. So what's going on? And anyway, that's just a warning. But what the story I'm telling here does make complete sense. But if you do try and go back and think of it classically, you just have to be careful, because something funny is going on, that you really don't have the usual kind of break up into configuration and momentum space variables that you're used to. Okay. That's all I wanted to say about that. Okay, so let's see. Okay, so that's all I want to say about the Hamiltonian. And I think I asked you in the problem set to think about more general Hamiltonians. What happens if you try to add an external potential? You add a different term than here. That if you try and add a interaction between particles, you get higher order terms. So there's a whole long story about how to doing much more complicated manipulations with these operators and the Hamiltonian. But let's get on to get back to some things are in some sense simpler, because this is this is a story about a very simple group action, just action by the real numbers. So the group, as a piece of group theory, this is kind of trivial. The Lie algebra is just the real numbers. There's just one. Its representation is just given by this one operator. It's it's a abelian group. All its representations are one-dimensional. All the energy eigenstates are one-dimensional, but they've got but the space is huge. So let's talk about some more interesting things that are more interesting as groups. Okay, so the first example was GW1. And so this is what happens to the so solutions have a symmetry. And the psi is the e to the minus I. Okay, and then the psi. Or you could also do this on the Fourier transforms of these, which are the momentum space, things which are called alpha or alpha bar. Right? So these are in some sense your coordinates on H1 on the space, and what you've got is so you've got this phase transformation symmetry on these things. And if you look at the way you've written down if you think about what the Poisson bracket is in these guys, it's a kind of a ZZ bar is equal to I kind of thing. Well, you're going to have, if you multiply, the Poisson bracket is going to be invariant under these transformations. And so this U1 lies inside this kind of U infinity of kind of all unitary, which is inside SP infinity. Anyway, so this is kind of the simplest model. This is maybe even simpler than the real number transformations for the Hamiltonian, which also lie inside this space. Well, this is even easier. It's just these overall phase transformations. And then you have to figure out what Okay, you have to figure out what would operate, so the course, but you have to figure out what's the corresponding, so corresponding to this action, what's the quadratic function corresponding to this guy. And I think I won't go through, maybe not, let me not go through this. So then what you do is you find the moment map. And that's going to be, actually, I'm worried that I have to keep track of my eyes. Moment map. The moment map, and then you quantize. And what you get is okay, so you're going to get, so there's two possible, you get, let me kind of, maybe it's a good time here to say something about this. You get minus I over 2 A, sorry. Actually, maybe let me. A dagger P A P plus P, or the normal ordered version, which is minus I integral infinity to infinity. Okay, so this guy, what this is. I mean, this is really actually exactly the same story as if you were doing the as what you had in the Hamiltonian, except it's even easier. You don't have these factors of p squared over 2m on the different modes, but you just have this guy, and this guy as well, this operator is what we'll call is this is the number operator. All right. So this, in some sense, is something much simpler than the Hamiltonian. He's just the thing which kind of counts the number of anyway. It just counts the total quantum number. And so again, to make rigorous sense.
So regardless of their energy, right?
What?
So regardless of their energy.
Yeah, so this doesn't depend upon the Hamiltonian, remember. So this is just kind of something that actually, any theory that you have that's got this kind of symmetry, which, if you like, your Hamiltonian function has the same number of psi's and psi bars in it, so that when you multiply the psi's by this and psi bars by this, you'll have a your Poisson bracket, and your Poisson bracket has the same number of psi's and psi bars in it. It has this kind of behavior, and now if your Hamiltonian also has this behavior, then what you're going to have is you have so H has has the same number as matching psi bars, so invariant under G U1. Then what happens? Then you have n hat. Okay, so this kind of structure here, you have totally independent of the Hamiltonian, or what the Hamiltonian is, the thing that's going to tell you about how you evolve in time. It's going to tell you physically about the energy. This is just going to count quanta. Okay, and you've got and so any theory in which you've got any theory in which the Poisson bracket has this structure that it's going to be invariant under these EDI theta transformations, you're going to be able to create to find this number operator. And you're going to be able to assign, if you diagonalize, you can diagonalize it, and you can assign assign this integer number, which is the representations you get of U1 to every state. Now, if in addition the Hamiltonian if the Hamiltonian function is also invariant under this guy. So if you've got one of these Hamiltonians that has, like the Hamiltonians that I wrote down now had a psi and a psi bar, so they have this behavior. And if you start adding interaction terms, as long as your interaction terms have the same number of psi and psi bars, then you're also going to have that the Hamiltonian function is invariant under this guy. So classically you're going to have this. Anyway, so classically you have that the generator of U1s kind of Poisson commutes with the Hamiltonian, with the generator of time transformations, and quantum mechanically the thing which is going to tell you what that generates the thing which infinitesimally counts the number of things, and the thing which infinitesimally counts the energy are going to commute. But so this is certainly true for the free particle one I wrote down, but it's true for a much more general thing. But it's not necessarily true. You can write down Hamiltonians that don't preserve particle number. And so if you like, and this is very interesting in in more in condensed matter physics, you can study systems where this Hamiltonian doesn't necessarily have the same number of psi and psi bars. It's going to not preserve. So particle number is not going to be a good quantum number that's independent of time, and then you have an interesting situation, and you get things like superfluidity and superconductivity and stuff like that going on. Okay, but does this make sense for this? And in the notes, I kind of gave a bit more motivation of this, going back to the going back to the finite dimensional thing and generalizing it to this. But I guess what I should say now, at some point I wanted to say, maybe I'll do this later, is just to watch out for this guy. So this guy, in some sense, is what we call the normal ordered version. This guy, I think I'll try to find at some point which to say some more about these guys. So this guy, if you look at it, this is really n hat plus a finite plus a shift. You have to watch out so what you're doing. I mean, you can change the order of these back, but then there's going to be a half here. So that plus, and the problem is it's plus an infinite shift. So the reason we don't work with this guy actually kind of group theoretically has much better behavior than he has. Anyway, he has better behavior because his commutation relations with other quadratic things are part of some bigger interesting groups, whereas you ruin that by doing it with this guy. But here the problem is that this guy has the nice behavior. He has the nice integer eigenvalues. This guy is integer some well-defined thing with integer eigenvalues you can make sense of, plus some hard to define, infinite shift, which you sometimes think of as a renormalization. And this is just one of the first places that kind of the bad news, the bad news about the infinity of this phase space starts to creep into to deal with. So one thing you're dealing with, anyway, I'll maybe say more about this later, but even in the simple case, by doing this rather than this, you're keeping it, you're making a lot of things well defined, but this problem you may come back and see this problem in more sophisticated situations later. And there's this whole business of what's called at some point I'd like to tell you a little bit about the so-called anomaly, and this is kind of where that comes from. Okay, so that's U1. You can do just quickly. You can. So this is what's called an internal symmetry. You're not taking You're not changing. X isn't changing here. You're just changing the values of you're operating the values of the fields. So you can do the same thing for so the free if you have n copies of this free particle, copies of the free particle. Well, let's just say n kinds. So I have psi of x, and but I may have a j index where j is equal to 1 up to n. So I can write down, if I have different kinds of particles, I can write down same thing. It'll be the same formulas except one copy for each j, and I just sum over j. So the different kinds of particles don't affect each other, but they all live together in the theory. Then you have a g is equal to u of n inside acting, and it's much like the U1. If you, in the case of one kind of particle, n is equal to 1, you have the U1. If you have two of them, then you have a U2, etc. And what you're doing is okay, maybe I can just write this out, and then you have so you get operators. And so what happens, how did I write? I wrote this down as like an xj. So xjk, I'm going to v of u of n. Say u of n, I guess. So in other words, so by this, I just mean the entries in an n by n anti-Hermitian matrix. Okay. And so these go to the representations of the symmetry in the state space are just a simple generalization of what you saw in the U1 case. They're just given by integral. So you're integrating over. You're getting one term for each p's. All the p's are behaving independently of each other. There's no everything is diagonal in the p's, and you're getting some. But now you have one, and you have creation operators which are labeled by both p and a finite index from 1 to n, depending upon the kind of particle that you're creating, and then xjk and an a k. So I think I guess I called this operator x hat or something. So on this kind of huge Fock space of all the different kinds of states with the of all these different multi-particle states, you have an action you have a unitarily algebra representation of UN, and this actually commutes. And one thing that happens is this guy commutes with the with this guy, because so this guy was really just the case of the kind of the center of this, the U1, which was just the trace of these matrices. So anyway, so this anyway, if you look at this guy, he's going to commute with any of these guys. And then what this says is that you've got a representation of UN on these multi-particle state spaces, but it's got it commutes with the thing telling you what the total quantum number is. So it doesn't change the total quantum number, but it can act non-trivially like this. It's really very much the same story that it's really exactly the same story you've seen about having these UN actions on the different energy levels of the harmonic oscillator, except it's just an infinite number of copies of that same phenomenon, which are independently happening for each P. That's really all that's happening here. And you have the same thing. And the formula is essentially the same for if you work in terms of in X space. In X space, it's just 1 to n. It's just so these are filled up. So you can write this guy in terms of in P space or in X space, and in X space again, it's completely diagonal in X. It doesn't. It's kind of a symmetry that's happening independently at each value of X. So that's kind of an internal symmetry, and again, kind of the same story. That if you start introducing, if you have n kinds of free particles and you start introducing interactions between them, you're then going to have some interesting story about, how many, which of these UN symmetries are going to survive, are also, which of them are also preserved by the interaction term. And so whatever interaction term you introduce, it's going to it's going to preserve some. This is going to be the U of n is going to be the biggest possibility to have. But it may have some smaller subgroup which is preserved, and then you can use the operators from that smaller subgroup to characterize the states of your system. And again. Yeah, and again, it's the same thing. So in the free particle case, you have X. Yeah, to make in the free particle case, this commutes with a Hamiltonian, and to make this, for this to be really kind of a really interesting operator, you typically want it to commute with a Hamiltonian, so you can kind of characterize energy eigenstates. If it doesn't commute with a Hamiltonian, then you say, well, it's not really. As a way of characterizing states, it's not very useful because, it doesn't. If your states obey this property at time t = 0, they're immediately going to stop doing it immediately afterwards. So who cares? Okay. So now let me go on to the spatial symmetries, and this is going to be. So I'll go quickly through this, and this is going to be your kind of problem set / midterm exam, is to kind of to do the couple calculations for these guys. But let me kind of outline how this is going to go. Okay, so space. What do I want to call this? A spatial symmetry. And so in some sense, what I mean here is that you have E3 X on H1. So one reason I spent a lot of time in the earlier part of this class last semester talking about the representation theory of E3 was that was that really what this is the reason for doing this? What was it was exactly because of what I want to do now. I really want to. So what I want to do is recall. well, that one H1, so the solutions, so the cells with P squared is equal to QFT with a fixed energy, give an n of U3. Okay, so what and the way, remember the way that we did this, so you had that on R3, E3x by, so x vector goes to R. Okay. So here R A. So this is an element of the Euclidean group is a rotation, a three-dimensional rotation, is something in SO3 or O3, or maybe I want to go to the double cover and do SU2, but it's one of those, and this is just an R3 of translations. So on the space, but then what we went is, so on solutions, acts by psi of x psi of R inverse. This is now here. This is definitely the inverse you're pointing at before. But this is the contravariance of if you have an action on the space and the action on functions of the space. That looks like that. Okay, and so now watch out that on okay. So this is on functions. So now where this gets here where it gets confusing is on distributions. And I think I was trying to, so here, so x, so if you think of this guy as a distribution, well, let me actually not write this out because the notation is going to get confusing. Just maybe say watch out. So watch out. And distributions x, by the inverse. So it goes to so here you're going to get us if this were a if you're thinking this is a distribution, this guy would be a psi of R. Again, you'd be back to this guy. So the confusing thing about it is if you notationally are thinking about these guys not as functions, but as actually as distributions, which you're going to feed a function to. Then the group action goes. You had to make it go in the opposite direction contrariantly here to get the action on the functions. You have to get the action on distributions. You have to kind of go back. So there's a horrible, and this may or may not have anything to do with that. With the same question about the time action, because here notice I'm just talking about spatial translations. I'm not. I've stopped thinking about time, and later when we talk about special relativity, and then we're going to try and put the time and space together. But right now, time and space have nothing to do with each other. There's a separate Hamiltonian talking about time.
So that's just because, like, if you give it a test function, you have some integral, you can change the variables, and you get.
Yeah, so yeah, exactly. You have an integral of psi of x, f of x, dx. And if this integration is invariant, then if you want psi of f to be invariant, it's like if you change this in one way, you got to change this in the other way. Okay, so now okay, so what happens? And this is the thing which I'm then asking you to work out in more detail. Is that what you end up with is this? Okay, so first let's do for translations. So you can think about these things. So we have to ask, what are the, this is, so again, you're going to have an R3, which G is equal to R3, which lives inside this kind of infinite. It's going to act by unitary. It acts by unitary transformations on the solutions, and you want to figure out what's the quadratic function that's going to give you the momentum. What's going to give you that? So you should get for each element of R3. You also have Lie G is also R3. For each element of Lie G of R3, you're going to get this operator, which is the infinitesimal, which is the unit. The unitary anyway, it's the infinitesimal generator of these unitary transformations that you get corresponding to these translations. And so what we're going to get is let me just write down some equations. You're going to get so we want an operator I'll call P hat, and so this is kind of also kind of a vector. Maybe I should put it in P vector, and it's an operator. It's got three components, and it actually let me just write down the answer, and what it's going to be is it's going to be unit over 3. So A dagger of P vector, A of P vector, and then P cubed P vector. And then it's just diagonal in the P vector. And as you would expect, the only possible thing this can be is P vector, right? It's good. What you're doing is this times these operators are counting the number of things with momentum P. And if you want an operator that's going to give you the total momentum, you just are going to sum over all P's, and the corresponding momentum times each of these number operators times each of the contributions from each of the states. Or so anyway, or if you Fourier transform this, it's going to be x vector, and then there's going to be a minus I. Okay. So this is what you kind of physically expect, and this is what so the trick is just to and so what you want to do is let me kind of stop at this point and say and what you really want to do is you want to use the commutation relations for your field operators to show that this is the operator that anyway this is the infinitesimal generator of translations on the on the states of your theory, or in the Heisenberg picture on the operators of your theory. Okay, and so then rotations. Okay, so now G is also 3. And again, now we want to find, so there's going to be a Lie G equal R3 for the basis, which I've been calling these LJ operators. And then and so knowing okay, so now if you want to this is the Lie algebra. These are just kind of 3x3 antisymmetric matrices, if you like, in the Lie algebra of SO3. Now, what we did last semester we spent a lot of time thinking about, you know, how do these things act? How do these things act on functions? That if you know, if these are infinitesimal rotations on R3, there's going to be an induced action on the functions on R3, and what's that going to be? And it's going to be given by knowing that the action induced on functions on R3 is infinitesimally, it's given by this L vector, which is there's a position operator with a cross product with the momentum operator, which you can also think, so you can think of this as being, if you want to work purely in position space, it's going to be x vector across minus I rad vector x, or if you want to work purely in momentum space, this is going to be I gradient with p vector cross p vector. Okay. So depending upon whether you want to work in position space or momentum space, you can use either one of these guys. And then you're going to find, I think this is the other part of this problem is that so you have so this is what acts on H1, if you like. This is what acts on the single particle, free particle solutions. What acts on the multi-particle state space is this guy. Will put a hat, and he's just going to be the integral over R3 of side dagger of x vector. And you can put you can use this guy plus or you can do it in momentum space, and it would be p vector then minus I. Okay, so that's the story, and so what? So now, so this is what you expect, and you can, and you need to show. You want to show L vector hat and P vector hat have the commutation relations. Oh, let me just say this. So they have the Lie E3 commutation relations. And two, where they commute with H. Okay. So that's pretty much, I think that's something else I wanted to say about, yeah, oh, I see. Oh, yeah. Okay, maybe I'll say a little bit, that's it. Let me kind of stop here. Maybe I'll say a little bit more about this. Is the there's a okay. So this is just the standard kind of free particle. Let me just leave that to start next time. And so let's take spinor valued solutions. Okay. But this story works anyway. This is the expected story. This is the story you get for the where H1 is the standard solutions of the single free particle Schrodinger equation, and it's got anyway. So this is the kind of generator of rotations on the whole big theory, on the whole Fock space, and this guy that I wrote here was the generator of translations. You know, these guys are going to commute with each other because they're just it's a abelian group. They're just different translations commute. These guys are going to have the SO3 commutation relations with each other. That Li, Lj is epsilon ijk, Lk, and then these guys and these guys. This is going to be the thing. This is then going to act by infinitesimal rotations on these guys, and everything is going to commute with the free part. You know, anyway, so as long as the free particle Hamiltonian is, you know, translation, rotation, and variant, so you'll get everything will commute with H. And then next time I guess I have to say a little bit about what happens with spinners. Maybe another thing to say about all of this is that, so everything here I kind of wrote down as assuming I'm talking about bosonic degrees of freedom. But if you look at what I did, everything that I did that I said makes perfect sense for fermionic degrees of freedom also. So if you say I'm gonna quantize everything as fermionic oscillators, and that these guys, instead of having the standard commutation relations, they have the standard anti-commutation relations, then all these formulas work perfectly, and it's still all true. Okay, so you can perfectly well talk about a theory, you know, a kind of a theory of free quantum particles, which happen to be fermions, and you're going to have this fermionic oscillator state space instead of the bosonic oscillator state space, but you're going to have all the same quadratic operators. I can look exactly the same. Okay, so that's about it. Yeah. So let me just say, so the things I didn't quite get to. Let me say a bit about this next time before we start. It actually, and then at some point I'll also maybe if I can find some time. Actually, you might want to, maybe I'd recommend just kind of more for general culture, looking at this next chapter, this, let me say, this is chapter 39. And really, one of the main points I wanted to make there, maybe I can just say, is that everything that all of this kind of works, a lot of what we've done kind of is based upon canonical quantization. Canonical quantization has this fundamental idea that there's really only one, up to unitary equivalence, there's really only one representation of the operators that obey the kind of Heisenberg commutation relations. And once you know the commutation relations, you don't have to worry about which representation you're talking to about, because they're all unitarily equivalent. Now, and that's the so-called Stone-von Neumann theorem. And that, but Stone, yeah, maybe just the thing just to note is just is that in infinite dimensions, there's no Stone-von Neumann. Okay, so one of these, so everything that I've talked about here so far has just been free particles. So in free particles, you do the standard. You do the standard quantization, and modulo this kind of some annoying problems with this infinite shift, which you can get rid of by doing by doing normal ordering. Everything's fine. But once you've anyway, this Fock space. So you've used the Fock space to create a specific representation that obeys the commutation relations. And you've got, and that works. But the problem is that in infinite dimensions, there's no guarantee. That's not the only. That's not going to be. There are going to be unitarily inequivalent and quite different kinds of solutions to this problem of finding something that your basic operators with their commutation relations act on in the right way, and depending on your Hamiltonian, may be well defined on the free particle Hamiltonian is nicely well defined, modulo the normal ordering on the standard Fock space. But if you decide to choose a different interacting Hamiltonian, what you end up finding is you find that the interacting Hamiltonian is actually not well defined on the standard Fock space, on the free particle Fock space. It's got various infinities, but there may be there may in principle be some other representation of the canonical commutation relations, which is unitarily inequivalent, and which is the one you need to do. So this is really kind of just warning you that in infinite dimensions there are various places in which kind of all hell breaks loose, and one of the fundamental reasons why all hell is breaking loose is because you no longer can rely upon this. But as long as I'm talking about nice, exactly soluble free particle theories, you don't see any of that. But the minute you start allowing things to interact when you've got and start choosing non-quadratic Hamiltonians in one of these theories, the infinite dimensionality of the problem is going to imply that you can have these non-unitarily equivalent ways of realizing the canonical commutation relations, and all sorts of kind of horrors can happen. So, and there's not even even being able to kind of classify what the possible solutions of what the possible representations are starts to become impossible, difficult or impossible. Okay, so I guess better stuff here. So I'll say a little bit more about spinors next time, and then I'll try to at least get started on move on to relativity. Okay, with any questions about any of this? I hope. I mean, again, there's more detail in the book. One thing to say is that I'm hoping that at this point a lot of the detailed calculations I did about how the Euclidean group works and how it acts on functions and how it acts on solutions of the Schrodinger equation, that all of that stuff which looks like overkill, that hopefully it pays off at this point, to which you actually can use it to kind of to say what's happening in these in this much more interesting multi-particle theory. Okay. Anything else now? Okay, well, definitely please come back and say hello, and we can talk some more. I'll be around for a while, but I'll shut this off. Bye.
Thank you, brother.
Thank you.
Bye.
Thank you.